Hi guys, let's deep dive into the fundamentals of blockchain. So, by understanding the three pillars of blockchain, which are the cryptography, game theory, and distributed computing, by individually analyzing their role and contribution to the technology. It's important to know that blockchain is an interdisciplinary field, hence, understanding all these three fields in detail is vital. There will be an individual session to learn them in deep. However, this session helps in understanding their role and presence in blockchain and a higher view. So, what are we going to do here? We are going to build a blockchain using one field at a time. So, basically, we understand all these three fields are required to build a successful blockchain network. So, using one field at a time, we will fail at a point. There comes the other field, which solves the problems which were unsolved by the first field. However, it leaves a few areas of problems which will be solved by the third field. Hence, the loop of building a successful blockchain network is closed. So, we will split the lecture into two different parts. One is understanding the problem and the solution. So, when we say understanding the problem, we are going to understand why the problem is tough to be solved and how blockchain solves it. And the solution is not just going to be a normal solution, it's going to be a pleasing solution. Let's see the bigger picture of the problem. So, there are three elements present here. One is trust, the second one is value, the third one is size. So basically, a trust is required for any financial product, financial model, or even for any economy. Say, for example, a, a piece of paper with the RBI's authentication is considered as a currency note. So basically, the RBI's trust gives the authentication for just a piece of paper to be considered as a 500 rupees value. If there is no trust, there is no value. For example, RBI's trust does not add up any value to the people, those who live in Pakistan. Hence, the value of the currency note is not the same in other countries, in a way. Now, we see once the value is added to a product, it can be used by or it can be accommodated into everyday usage of a large size of people. For example, an economy like India, you have RBI's backup and you have the value of a product. Now you can implement it to the public's usage, whereas a large number of people use the product. So most of the financial model and financial products or even government, they stuck with these three elements. The reason why I say they get stuck is in most of the cases, the third arrow, which goes from the size to the trust, does not fulfill. And that's the reason a government or any centralized authority, they pump in more and more of trust to increase the value, which keeps the size intact with the financial model. Now, once if we are able to close the loop, that is, once if we are able to convert the size into trust, then it becomes a successful financial model or product or economy. Now, if you remove any one single entity from the whole loop, it loses its value, or the whole cycle, it will not function. For example, RBI demonetizes any particular currency, then the currency loses its value, even though there is a huge amount of people using it. Or, for another example, any company or any financial institutions, they hype the value artificially. And when the users get to know that the hype is the value is artificially hyped, then once again they lose the trust, and once again the users numbers goes down. So you need a complete loop to have a successful financial product, and that is the problem blockchain has solved. So initially, blockchain they had, say for example, we'll take the example of Bitcoin. Initially, Bitcoin they hyped the value of the product, then it resulted in number of users. Now, Bitcoin has closed this loop, that is converting the user size into trust, and a part of the value is backed up by the trust. Hence, the loop is fulfilled, hence, the product is successful. Now, we'll see what the actual challenge in converting the size into the trust. Now, the challenge is converting the size into trust, which means we are going to distribute the trust, because the size involves multiple parties or multiple nodes. So, the trust has to be distributed. So, the biggest or the core problem in distributing trust is consensus. What do I mean? In a peer to peer network, there would be outrightly multiple malicious forces trying to disrupt the trust. Uh, Say, for example, according to the proverb, too many cooks spoil the broth, which means when there are too many cooks trying to come into an agreement on delivering something, there would be multiple disagreement, which will end up in spoiling the broth. So when we take this example in a peer-to-peer network, there could be a collection of malicious forces or nodes trying to disrupt the network itself. Hence, a Byzantine agreement is required. Once we have the Byzantine agreement problem fixed, we can have an agreement which converts the size into trust. Byzantine agreement is a core problem, not just in distribution of trust, but in any distribution of computing, with or without blockchain. When we implement distributed computing for storage, network, or anything, we require a collective agreement or disagreement on a protocol, and process is mandatory. Now, why are we addressing this agreement as Byzantine agreement? Is because in any collection of nodes or participants, errors are common, but there could be intentional viruses trying to bring down the agreement, which is called as Byzantine faults. Therefore, solving the Byzantine agreement is a core problem in implementing distributed trust, which helps in achieving the ultimate goal of converting the size into trust. The presence of physical broadcast, getting agreement is straightforward. For instance, if you want people to agree, just broadcast all the values and you can take the majority of the value. Finally, there is an agreement. For example, selection of a leader. Everybody votes and gets to see the majority of the votes and decides on who the leader is. However, on a peer to peer network, it is not the same. We have the major issue of Byzantine agreement here, which is the intentionally faulty nodes trying to disrupt the trust system. Now, even without the Byzantine fault tolerance issue itself, there are many other faults and errors. Say, for example, if a source A is trying to broadcast a message to B and C, now there could be an instance where A broadcasted the message to B and C. However, there was a power shutdown before the message reaches C. However, the message has already reached B. In this instance, it is a clear evidence that simulating the broadcast in peer to peer network, even without the Byzantine fault tolerance problem itself, is a concern. It turns out, even in a system of three people, if one of them is Byzantine fault, if one of them is a liar, it is impossible for the other people to find out who the liar is, and impossible for Byzantine agreement. Now, that's why the problem of blockchain becomes tough here, because blockchain has to deal with distributing trust with multiple nodes or people, which is the entire size present in the loop, which is in the later form converted into the trust. Now, if you take the example in this slide, you consider in the network alpha 1, where A is broadcasting, which is unicast of a message to B and C. So the input message is 0. So if you see the output of the message in network alpha, B and C confirms the same. If you take the network alpha 2, C is broadcasting a message, and the input of uh, A dash and B dash as 1 and 1. And in network alpha 3, B is broadcasting message 1 to A dash and 0 to C. Now, if you see the network alpha here, according to the network alpha 1, A is sent 0 to both B and C, which is the output shown here. And according to network alpha 2, C has sent 1 to both A dash and B dash. And according to network alpha 3, B has broadcasted 1 and 1 to A dash and 0 to C. Here, if you take the communication between C and A dash, the values which they output or they have received is different. However, they both have to agree on something which B has broadcasted. If we can show that agreement is possible here, then there must exist some other network which is self consistent. But no such network exists which is self consistent, and therefore agreement is not possible. To address the Byzantine fault tolerance here, if you take network alpha 3, B can act as a split personality and inform A that it has sent message 1 to C. However, the actual message sent to C is 0. Now it becomes really tough for A to understand whether B is the liar or C is the liar. Here brings in the Byzantine fault tolerance issue. The one way we can solve this issue is by implementing a digital signature. And that's how cryptography comes into the picture here. So, if the message sent by B is cryptographically signed, then A can confirm whether B is liar or C is a liar. So we understand that we require distributed computing to solve the problem of converting the size into trust. However, the basis of agreement itself a problem here, and that's where Byzantine agreement comes into the picture. And to solve the agreement or the Byzantine agreement itself, we require cryptography to sign the messages sent by each nodes to confirm and have a trusted network. So we have a computationally secure digital signatures here, and that's good enough to get you a computationally secure Byzantine agreement. And that's how distributed computing and cryptography comes here to solve the problem of consensus. And the third field, game theory, comes into picture, especially when the account or the participants of the node is not in a controlled environment, which means a blockchain network might not know who are all the participants in the network itself. People might add on, people might get out of the network. Hence we require a game theory to calculate the number of agreements to make a decision on the consensus. Hence, you can see the three fields can be mutually complementary to each other to form a successful blockchain network. Now, let's experimentally see how all these three fields come into picture. They combine together to make a practical and an experimental blockchain network.